Let's go with the theme song and the intro now. Teach me about the Great Lakes. Teach me about the Great Lakes. I forgot to ask if you could hear that. Could you hear that?
Yes.
Perfect. Welcome back to Teach Me About the Great Lakes, a twice monthly-ish, with an emphasis on the ish podcast. Let me try that one again. What do I even say? Welcome back to Teach Me About the Great Lakes, a twice monthly podcast.
In which I, Stuart Carlton.
Ask people are smarter.
Would you like me to do it for you?
Oh my God. Wow, this is where we are. The thing is, I started thinking.
No, I'll do it. That'll be fun.
Yeah.
Okay.
All right. So you're going to do it?
Sure.
All right. Teach me about the Great Lakes. Teach me about the Great Lakes.
Welcome back to Teach Me About the Great Lakes, a twice-ish monthly podcast in which I, Stuart Carlton, get people who are smarter and harder working than me to teach me all about the Great Lakes. I am Stuart. No, I'm not Stuart Carlton, but Stuart Carlton is here.
My name is Stuart Carlton, and I now remember the introduction to the podcast. And I know a lot about asking Carolyn, what is the introduction to the podcast that we have not had a regular schedule for approximately, I don't know, 1 year, but I don't know a lot about the Great Lakes. And that's the purpose of this show. In fact, I'm joined today by the one, the only, the special, Caroline Foley. Carolyn, what's up?
I'm channeling you today, Stuart, so I will talk in more emphatic noises.
Oh.
I'm doing well. I'm excited for today's show because it's one we've been hoping to get going for a while.
Yeah, it has been a while. Am I overly emphatic? I could be less emphatic if I need
No. I'm just being silly.
All right, that makes sense. Well, anyway, yeah, I'm excited too. We have been waiting for a while to talk to today's guest, and we're going to talk about something that I knew a lot about when I lived in Florida, but I didn't even know it was a thing in the Great Lakes until recently. And that thing is bull sharks, is largely what we're going to be talking about today.
No, we are not talking about bull sharks. We are talking about sinkholes.
Sinkholes, that's what it was. Also in Florida, where I learned about that. Maybe we'll get into bull sharks potentially, because who knows? But anyway, let's just go straight to it. First, of course, since we're speaking with a researcher, it's time for our researcher feature. Researcher feature, a feature in which a researcher gonna teach us about the Great Lakes. Our guest today is Dr. Bopi Biddanda. He is a professor of water resources at Grand Valley State University in the Annis Water Resources Institute in Muskegon, Michigan, home of drowned river mouths out the wazoo, or the Kalamazoo. Anyway, Bopi, how are you today?
I'm very good, and I'm very excited about this. I have a feeling this is going to be even more fun than the sinkhole research I do out there.
That's probably not likely.
We'll do our best. Well, so let's talk about that, actually. So sinkholes. So I did know that they existed in Florida. I lived in the St. Petersburg area, and every now and again, a sinkhole would open up and, like, swallow your yard, maybe a dog, often an alligator or whatever. So do they have, my understanding is you do research on sinkholes in the Great Lakes. Do they have sinkholes in the Great Lakes?
Yes, they do. It's not uncommon to find sinkholes on land, like in Florida and the Yucatan Peninsula, which are basically slabs of limestone karst, which are very porous and dissolvable sedimentary rocks, mostly made out of carbonate. You find on-land sinkholes around Alpena, Michigan. Which is topped by limestone. We have our largest quarries out there for limestone, and you can see them if you fly in an aircraft near Alpena. You'll see on-land sinkholes that are perfectly round with water in the bottom, rainwater and groundwater. But what we study is submerged sinkholes that pop up in the bottom of the Great Lakes. Yes, there are many of them. We have only studied a few. We bet there are hundreds, if not thousands of them in all four of the Great Lakes, which are underlain by limestone karst.
So that's a requirement that for them to form is this karst layer?
Yes, a karst layer seems to be a requirement because karst is the most porous of rocks. By that nature, it makes it very precious for humankind because they, in fact, roughly 50% of the wells in the world go into karst aquifers because they're very spongy. They hold a lot of water. In fact, and the dissolution creates caves and caverns and spaces where water can fill. But also water dissolves. That's why you have sudden giveaways where you have a house swallowed up or a road falls down and things like that. But a similar thing can happen underwater where, groundwater percolates down, rainwater percolates down through karst conduits, and then it hits a different bedrock, like one of those, non-sedimentary rocks that are being cooked in the belly of the earth that don't yield anymore. And so, there's no more down to go, so it climbs up. And it can pop up below the Great Lakes, which are still, limestone. And over time, dissolve it, and then groundwater start pouring out.
Oh, okay. That's wild. Okay.
And if in my studies, so those are just sinkholes being created by groundwater dissolving limestone at the bottom of the lake. But if this groundwater goes through Paleozoic marine evaporates, by which I mean 400 years ago when Michigan was under the sea, and where the seas have left behind their salts, Paleozoic evaporates, then along the way they pick up the salts, especially sulfates and sulfur. And if the conduit is long enough, they lose all their oxygen, because any organic carbon that's in rainwater and in soil and in the ground is respired away into carbon dioxide. So there's no oxygen, and high sulfate from the marine evaporates, it picks up, and that creates a whole new stage, a stage similar to what early Earth was. It's when its shallow seas were had almost no oxygen, in fact, no oxygen, and were high in sulfur. So lo and behold, when water with the submerged the sinkholes pops up, but carrying these marine evaporate salts, high sulfate in particular, and has gone through a long conduit where all the oxygen is gone, then it creates those primordial conditions, and there you will see proliferation of microbial mats, just like maybe how it was in the early biosphere. And we think their reflections provide a view into how the early biosphere might have been and how that might have led to oxygenation of our planet over a long time. I'm talking 2 to 2.5 billion years.
So there's a lot to unpack here. So essentially, as the water forms these sinkholes and picks up the salts, and if it sort of has this primordial gumbo down in the bottom of the sinkhole, essentially, you say that it leads to the formation of a microbial mat. First of all, what is a microbial mat? Is that, I think of a mat as something that's like stitched together or a thickness. Is it that, or is it just so many that are close together it looks like a mat?
That's a good question. Mats, you can imagine them almost like a carpet in your home or the throw rug. And these the first cyanobacteria that that came about and learned how to do photosynthesis, or filamentous. And by nature, they became mat formers. They would weave in and out and expand, seeking better habitats in the shallow seas of the ancient seas. Between around 3 to 0.5 billion years ago. So they would crawl around and view mats and cling to the surface. Probably they clung to the shallow seas where at the depth where UV was not too strong, but not too deep where there was no light at all, so they couldn't photosynthesize. And we find the same kind of system in Lake Huron sinkholes, where the mats are very motile, the filaments. In fact, they can run tens of micrometers in minutes.
Oh my gosh!
Even though they're only about 5 to 10 micrometer thick, they can run, in terms of body length, they can run faster than a cheetah.
Oh, that's awesome!
It's very fascinating. So they're they're Speedy Gonzales. They most rapidly move at the turn of the day and the night. the photosynthetic filaments move rapidly upward, seeking sunlight at dawn. And there are chemosynthetic ones that are probably even more ancient than the photosynthetic ones, because at first there was the very first life supposedly learned how to crack the chemicals, preferably around the thermal vents in the sea. Okay, where the sulfate-rich environment, there was no sunlight, but the sulfur, they could crack H2S, just like photosynthetic organisms now can crack H2O, the water. So there's the sulfide water analogy. So those organisms will climb up at night to the mat surface. They're white in color or pigmentless. So the mat, they're seeking hydrogen sulfide that's been generated in the sediment at the surface and harvest, so they can chemosynthetically grow. And at dawn, the photosynthetic ones migrate up and harvest the sunlight to photosynthesize. So you have this day and night shift where it's purple during the day and white at night. So it's pretty dramatic. We call it the 1 millimeter journey. After that movie, the 100-foot journey, we call this the 1 millimeter journey. But to think that for the longest time ever, 2 to 3 billion years, this 1 millimeter journey might have been the largest mass movement of life on the planet. That is amazing. Right now, it is the zooplankton that migrate hundreds of meters all over the planet, including the Great Lakes. During the day, they go down to hide from predators and UV. At night, they come up to feed on the phytoplankton and not be picked up by visual predators. So zooplankton are the biggest mass movement of life on the planet daily. But to think that these microbial mats might have been doing those 1 millimeter journeys for a long time, and to think that might have been crucial for their success in a turbulent primordial ocean, being able to stay on top with the way the biochemistry changed, they could be on the top and harvest sunlight at the same time. You'd think it's probably was the very first tango in life.
That's wild.
Well-coordinated daily dance. Yeah.
That's fantastic. So do you have images of like a daytime mat and a nighttime
Yes,
mat?
we have. And they are available in that EOS, or American Geophysical Union article we published. And the last time we were out there, a year ago, we put a time-lapse camera down there and had them go take half an hour snapshots through day and night. Oh, it is dramatic to watch this turn, go purple during the day and switch to white during the night. And then back in the lab, divers collected intact cores, with sediment, with carbon-rich sediment in the bottom and a thin layer of intact mats on the top. And we have this, what is called a microprofiler. You all know about this, like oxygen probes and temperature probes, like thermometers and so on, that we can use to measure a water column. But these microprobes are so thin, they're only as thick as your hair, just 100 micrometer thick. And with an automated programmed motor, you can tell them to go only 50 micrometers at a time. So they can go, they can have 20 intervals in a 1 millimeter mat. So they can probe from the water to the mat, through the mat, down to the sediment. We have classic day-night profiles of how, oxygen increases during the day towards the top of the mat, and hydrogen sulfide decreases then. And at night, things reverse. Hydrogen sulfide increases, oxygen declines. So that's what these organisms are making and optimizing their position for.
That's so cool.
So that's a very nice synchrony, and we published that in the Journal of Great Lakes Research last year.
So we'll have those links. I think this will wind up being episode 99, or it might be 98, but it'll be in the show notes. and at teachmeaboutthegreatlakes.com. I have one question. So you mentioned divers. How deep are they diving that they're collecting the cores that you then bring back to the lab and do additional studies on? How deep is the location that they dive to collect those cores?
Very good point. This is something I should have stated at the beginning. Sinkholes occur at all depths.
Okay.
So we have a natural gradient. There are ones in El Cajon Bay, 6 miles from Alpena, Michigan, in the Thunder Bay National Marine Sanctuary, where you can wade into gurgling springs, in El Cajon Bay. You can see them on the surface. They're a meter below or so. The groundwater comes, and it is popping out because due to hydrostatic pressure and creates rings on the surface. So you can see something is bubbling out there. And it smells hydrogen sulfide there, just like how the early Earth probably was a stinky place, where life first began. And then down at the very bottom, you see purple and white filaments wafting in the groundwater flow, and patches of mats that are clinging to the lake flow. Everywhere else, the lake is different. It's got this, green algae, large macrophytes growing, and then phytoplankton in the water. But here, it's very different. No oxygen, high sulfur, and only microbial, like how it might have been in the early part. There was no room for larger organisms and complex organisms because it was oxygen-less. Yeah. So we have a gradient from these shallow wadable springs to the one we have studied a lot, which is diveable at 23 meters. It's at Middle Island. It's an island about 6 miles offshore of Rockport, Michigan, north of Alpena. There we can dive down. You see, there's just next to Middle Island on the north face, like a horseshoe shape in the shoreline has been carved out. That's where the sinkhole formed, and groundwater gushes out in a pot and pours out and spreads out. It's created amongst the huge boulders of karst of limestone that are the size of a bus, and you can see this cavern where groundwater is pouring out, and then down below it's these colorful mats which are purple during the day and white at night. So divers have a ball with this, and there's an underwater waterfall because groundwater flows over a sill and goes down about 10 meters into the up to from about 10 meters up to 23 meters to the lake floor. So you can kind of surf the underwater waterfall. All around you is suddenly it's like a painting, tapestry of colors. Okay, just until you get maybe it's the size of a football field until you get to the edges where it again gets to be boring, Great Lakes floor. And there you can see fishes and invertebrates and all trying to grab a piece of the pie, because it's reasonably oxygenated because now the groundwater is mixed. Yeah. And the groundwater is salty and also low temperature. So together it helps them cling to the bottom. So it's a constant, almost like a chromatograph, condition that helps the mats thrive. From the source, groundwater comes out, it pours out and spreads from its center outwards. So it can be as thick as 5 meters at the origin and then down to almost nothing in a distance. So metazoans and higher organisms, fishes like barbot and other fishes will try to nibble at the periphery, but they cannot really come into the microbial world. So then we have offshore sinkholes, where it's here in the 23 meters, about 5 to 10% of light gets down. 5 to 10% of what hits the surface gets down. So they can be photosynthesis. And efficient photosynthesis because cyanobacteria are masters at harvesting low levels of light with their, phycocyanin pigment and accessory pigment in addition to chlorophyll. But There are offshore sinkholes, aphotic, at over the 100-meter isobath. There's no sunlight. So you kind of have the photosynthetic cyanobacteria. You only have the chemosynthetic white or pigmentless filamentous archaea and bacteria that make chemosynthetic carbon, just like what happens around the thermal vents and cold seeps in the sea. And so they are white in color. There's no other pigmentation, no green or purple there. So that is also fascinating to think that we have analogs of the deep sea vents and seeps right here in the Great Lakes at just 100 meters. We're not talking about 1,000 or 10,000 meters. We're talking about 100 meters. And in fact, we have genetic information from genomics that show Bigetova, which is one of the dominant sulfur oxidizing groups, those filaments are here too. The same genus, but we don't know if it's the same species with the same genus. So there's a lot of these parallels to deep sea. Everywhere you go, even on land or freshwater, we see marine connections because I think that we're still an ocean planet. So, in this case, it's the memory of the old seas, the salts that are fueling these mats under the water. So there's a gradient of them. And I should mention before I forget that, for a long time, we were only been studying the Lake Huron sinkholes. We always suspected from anecdotal stories from divers from Ontario, from Lake Erie and Lake Michigan. Oh, my family went diving here and there and we found purple mats, and they were even sent some pictures and so on. But recently we've done some scientific studies that show that there's definitely sinkholes with purple and white mats in the Lake Erie Basin.
Which part of Lake Erie?
It's Monroe County. It's the southeastmost corner of Michigan. Okay. Right by the shore.
Okay.
Yeah, it's called the Great Sulphur Springs. It's been engineered now because there's farming and other things around it, but the sinkhole still is there, and the mat still seems to process. Again, it's high sulfur, no oxygen water, high conductivity because of the salt. At the very bottom, there's these purple mats that are, and it's fascinating because during the late growing season, the mats, the carpets, they kind of pull up into little hills because the sedimentary gases, methane builds up and it's buoyant, so it pulls up the mats. And in places, you can see them even torn off. We think that's how the mats actually disperse. They get torn off, and then they float to the surface, and then they could land in the beach, dry up, and get air carried, or become part of the water current in the Great Lakes and go places. Yeah.
So do they rehydrate later and kind of reestablish
in the lab? We have seen my students are actually running an experiment, a torture experiment, to speak of, torturing them in different ways and seeing if they revive.
Oh wow!
Dry them for different times at different temperatures, and then see if they revive. And the initial indications are that they rapidly revive. They hydrate, and the pigment colors come back. My students tell me they even start moving toward, like if you put them in a petri dish, hydrate them, you give them only a pinpoint of light, or cover them in aluminum foil, but only give them a pinpoint of light in one corner, and you see them moving towards that, over hours and days. So they say there's indications they are already moving towards that. So these are all encouraging signs that they're tough. Probably why they made it through all this deep time and are able to disperse. In case you didn't know, the closest analogies to these purple mats and the hills they make, the little, we call them Purple Ridge Mountains, like the Blue Ridge Mountains, although these are only a foot high or so, have been found in the Dry Valley permanently ice-covered lakes of Antarctica.
Oh, wow.
And the National Science Foundation has a program studying them as analogs for possible, extraterrestrial life we may find, under the icy oceans of Europa, for example. Yeah.
That is so cool.
So these are really, it sounds like dynamic systems, right? And I think a lot of your work probably is just using this as an analog, like you were saying, for early conditions on Earth, because it's a way to sort of look back into prehistory or primordial times. But what is the relationship between the sinkholes and like the lakes more broadly, if that makes sense? Like, is it a source of nutrients or something for other organisms within the lake, or how do they affect the broader lakes in general?
Yeah. This is a very important line of inquiry we've just started. We don't even know the age of groundwater that's popping out. Not only we know something about the composition because we measure the nutrients and conductivity, sulfate content, and nitrate and phosphorus content and those things. But yes, what is the contribution of sinkholes? Groundwaters are big contributors to the lakes, often ignored because we only measurable surface water flows. There are USGS studies that show that groundwater contribution to the Great Lakes dynamics is almost as important as the surface runoff into and out of them. So these are big. What portion of that is sinkhole derived? We don't know, but I think it's definitely at and around or maybe more than 1%.
Okay.
Depending on how numerous they are. There's very little reason to think they're not thousands, if not hundreds of thousands, in all over the Great Lakes, which are limestone based.
Sure.
Yeah. So we're also worried about contaminants that could go rapidly from anthropogenic sources on land to distant sinkholes, or even in terms of conservation, we are worried also about what happens if we pave over a potential, rainwater source for a distant sinkhole. Do we just choke it? There's all these considerations. So we're trying to quantify the age. Preliminary information is they're a mix of old, ancient water and new, but tending towards more recent, because they have signals of sulfur hexafluoride, SF6, which is a anthropogenic production, made for, or as a refrigerant and so on in the last 60 years or so. So dominance, the major indication seems to be there a mix of old and new water, but the new water is showing a dominant signal at least in the about 3 sinkholes we measured. So they might even reflect rainfall on land with a lag of few weeks or days.
So here's the depressing questions, and I got 2 of them. One is, have you figured out whether or not sinkholes are loaded with microplastics? And then the related question is, what % of sinkholes are PFAS, do you think, at this point?
Yeah, if our initial signals are that these are not receiving predominantly ancient water, meaning millennia or more, they would be actually very good sentinels for looking at some of these modern anthropogenic contaminants, because as it's very possible they have not yet got them or are just beginning to be contaminated with both the ones you mentioned, plastics and PFAS, the forever chemicals. So those would be good sentinels to start looking at now, and they would be great observatories. That's what I think, as an indicator of change up and above in the terrestrial biosphere, because they're just kind of distant and removed as of now, but probably not for too long. Yeah, because they are intimately connected with the surface above.
It's almost like you can do time travel where you're going back and forth. That's really, really cool.
Excellent. Well, Bopi, this is really interesting, and I could sit here and listen to you talk about sinkholes all day.
Genuinely,
yes. And your knowledge is amazing, and your poetic way of speaking about them is inspiring. But that's actually not why we invited you here on Teach Me About the Great Lakes this week. The reason that we invited you on Teach Me About the Great Lakes is to ask two questions, and the first one is this. If you could choose to have a great donut for breakfast or a great sandwich for lunch, which would you choose?
I'm not a big donut person, so I'll go for the sandwich. I mean, Muskegon here where I live has a lot of good places, good eating places. I'd go for Fatty Lumpkin's Sandwich Shack, which is a walking distance from here. And me and my lab mates often go over there for a bite to eat.
There we go. All right, so when I'm in Muskegon, looking at the Drowned River mouths or what have you, and I go to Fatty Lumpkin's Sandwich Shack, what sandwich should I get from Fatty Lumpkin?
Oh, yeah. I don't remember. Many of their chicken sandwiches or beef sandwiches are just very, very good. Yeah, I sound like a promotion. Yeah.
Oh, yeah, well, that's what we're here for. Yeah. All right, I'm going to their website now. No, I don't want you to lose my location. All right. Well, I'll let you know.
Okay.
Yeah.
Okay. And that's great, and that's just a great name for us.
I wonder who Fatty Lumpkin is.
It's a small little hole in the wall place, but it's
They're the
really
best.
good.
Okay, so the second question we wanted to ask is, what is a special place in the Great Lakes that you'd like to share with our audience, and what makes it special?
I mean, if it's related to the sinkholes, I would definitely say the Thunder Bay and the Thunder Bay National Marine Sanctuary. It's an incredible place because you have, wealth of shipwrecks there, maritime history, and the sanctuary it's one of the first and I think one of the second in the freshwater system. They're marine sanctuaries. There's Wisconsin has one now, but this has been there for a quarter century and it's full-fledged. Great maritime museum for visitors, and boats can take you out to see shallow shipwrecks. And I guess you can go diving with sports divers to visit some of these shallow sinkholes as well. So I would call that my favorite, but I definitely have to put in a pitch for where I am, the Drowned River mouth systems. There's something over 24 of them along West Michigan. And they're all I'm a carbon cycle person, a microbial ecologist. They're all hotspots of carbon cycling. These estuaries are at the end points of major watersheds, small and big. Muskegon, it drains the second largest watershed in Michigan. They're a great balance between the less productive rivers, which are nutrient rich but are turbid, so light doesn't get in. But when the water comes into these drowned river mouth estuaries, they find a great balance. The opaque particles settle down, and the phytoplankton see the nutrients, and they go to town. They make organic matter. They can make food, and fishes and other things. Food web thrives in them. And the residence time of a week to a couple of months in these systems is just right. So things don't get just flushed out, but they can complete life cycle. So we have some of the best fishing grounds in all along these 24 drowned river mouth estuaries. And it's wonderful that they also make good places for harbors. And they are great, places for people to live by the water in major estuaries. Okay, they also are problem sites because of anthropogenic impact. Okay, so we have this gradient of north to south. Less anthropogenic impacted to more anthropogenic impacted systems. We're trying to make this wealth of naturally and anthropogenically impacted systems as argued that it be one of the national estuarine research reserves. We're hoping we have a petition to the Michigan at Michigan, and to forward it to at national level. Hopefully it'll be successful, so we can invest in studying these, very biodiverse and They are basically carbon cycling hotspots and fisheries rich and people rich places. Hopefully we can study them better and invest in long-term conservation of these water bodies. Yeah, drowned river mouth systems. And our institute is right at the bank of one, Muskegon Lake. So, and we can see Lake Michigan from here. It's one of my favorite places.
Fantastic. Well, Dr. Bopi Biddanda, the professor of water resources at Grand Valley State University at the Ennis Water Resources Institute in Muskegon, Michigan, home of Drowned River Mouth and, of course, Fatty Lumpkin's Sandwich Shack. Thank you so much for coming on and teaching us all about the Great Lakes.
Thank you.
Well, that was excellent. So cool to hear somebody talk so passionately about sinkholes, which, A, I barely know were a thing, and B, I had no idea that they were so fascinating and so prevalent in the Great Lakes.
Yeah, it's this is the primordial soup is just like I just made the head exploding thing because this is a recording.
It was a little,
that was really fun.
For those of you, not watching, which is everybody except me and Carolyn, she did
I did the explode. Yeah, but it's also, it just makes me think of that quote that it's bacteria's world and we're all just living in it, or like it's microbial world and we're all just living in it. It's like, they will survive. They will survive.
They will. Yes, they will. It's interesting to talk to because he's a water guy, right? And so I'm like, what influence does this have on the broader Great Lakes? And I'm waiting to hear about salmon and if everything goes wrong, maybe you'll hear about like Lake Sturgeon or whatever. But instead, it's all varied water. So it's good to get that diversity in terms of how people think through science as well.
Yeah, and it was also, so we were talking about the drowned river mouths, like along there, and that was one of the first places I ever did field work, a number of years ago when I worked with Jan Subrowski, and they're just stunningly beautiful. Like they're gorgeous.
Drowned river mouths are?
Well, like the surrounding area, I was there in, if you go there in like fall or late summer, you start to get these beautiful colors, and it's just like, they can be really, really pretty. Muskegon is a really big one. It's also like really interesting, but some of the smaller ones along the way, or like there's a wetland that is just barely connected and things like that. They're really, really pretty. And so in my head, I'm like, yeah, they're pretty. And he's like, they're so interesting from like a carbon cycling. And I was like, that's awesome. That's just awesome that there's so many ways to appreciate them.
Yep. So we got a little confession time.
Confession.
I have no idea what a drowned river mouth is. I go to every one of Thomas's students' presentation, and they start talking about drowned river mouths, and I'm like, oh, a drowned river mouths. That sounds nice. So, for today's Great Lakes factoid, Carolyn, why don't you go ahead and help me understand what a drowned river mouth is? It's a Great Lakes factoid, a Great Lakes factoid. It's a great factoid about the Great Lakes. Cha!
I feel like I'm in Bill and Ted or something. We're talking about time travel. You've got crazy. Anyway, okay. So, a drowned river mouth in the Great Lakes. It's like, when I was first introduced to them, it was as like a drowned river mouth wetland, but that's not necessarily the case. They can be a lot bigger. They function kind of like estuaries, but it's all fresh water. So it's, along the edge of the lake. Conditions in the landscape and stuff like that are such that you have this kind of area that gets flooded. So if you look at like a GIS map of it, you've got all these little kind of like there's a river that comes in, and then there's a spot where there's just a whole bunch of other water, and then it goes out into the lake. And you actually can see signals that they do kind of like the way an estuary on the coast, like of the ocean, you can look at like the salt water. So like there's a freshwater river coming in, and then there might be a mix. And then when you go out to the ocean proper, it's salty. In the Great Lakes, you don't have, salt water, but you can see like pretty distinct signals in other in a whole bunch of other things that they are fairly different habitats. So it's basically like an estuary.
There we go. And that's why they're interesting to study. Excellent.
Yeah. And any place that's like an area of transition and change, I feel like scientists are like, or ecologists are like, yes, that is where I would like to study.
That's what I did my senior project on one of my English classes was transitional areas in Jazz Fest audiences in New Orleans. And I tried in a very half-assed way, probably can't say that. I tried in a very half-hearted way to make connections between the ecology I was learning in edge communities and like edge communities at the different stages at a music festival. So transition is interesting.
Yep.
Speaking of...
Teach Me About the Great Lakes is brought to you by the fine people at Illinois Indiana Sea Grant. We encourage you to check out the cool stuff we do at iiseagrant.org and at ILIN on Facebook, Twitter, Instagram, and other social media. I think they're really up in their Instagram names, so we got to add that in.
Our senior producer is Carolyn Foley. Teach Me About the Great Lakes is produced by Megan, the Lake Lover Gun. Rainey Miles. Ethan Chitty is our associate producer and our fixer. Our super fun podcast artwork is by Joel Davenport, and the show is edited by Sandra Svoboda.
If you have a question or comment about the show, please email it to teachmeaboutthegreatlakes@gmail.com or leave a message on our super hot hotline at 765-496-4474. And then I wonder, do people actually read this? But that's part of why I do the goofy things here. Okay, listen to it, not read it. You can also follow the show on Twitter at Teach Great Lake. Either way, thank you so much for listening, and keep grading those lakes.
Beep,